Welcome back, students. As we saw in the last lecture, with probability in statistics, we're often considering discrete variables. For example, we can roll 1 die, 2 dice, 10 dice, but we can't roll 1.5 dice, right? That doesn't make any sense. This is true for games of chance like we've been discussing, but it's also true for molecular systems that are made up of individual molecules. So we can describe any large collection of molecules as being made up of individual units of molecules. So in the same way that we can't flip half a coin, we can't talk about the energy of half of a molecule. At some level, discrete variables become cumbersome to use, and we'll see why that is in the next couple of slides here. For example, if instead of having a nice small number like 1 or 2 or 10 dice or coins or molecules, what if we had 60 sextillion, 221 quintillion, 409 quadrillion objects? Then it would be very challenging to use discrete variables to describe this many objects. In fact, it would be much easier to say that this is 0.1 moles of that object. So instead of using a discrete variable, the number of actual molecules, we can use a continuous variable that is the number of moles of substances that we have. So we can convert discrete variables like molecules into continuous variables in this way, and we'll see how to apply that using probability. So the learning goals for today are going to be to plot the probability. We'll use both the binomial distributions and the Gaussian distribution. So we discussed the binomial distribution last time, and that is a discrete variable where we have yes or no, success or failure as the only two outcomes. We can do a similar thing with the Gaussian distribution, except for the Gaussian distribution is a function of x, so it is a continuous variable. And then we'll also consider this contention, and we'll see why it's a little bit contentious, as to what happens when we have a large number of molecules or any other object. So we kind of have this idea that as we increase the number of events that we're counting, so for example, if we flip 1,000,000 coins, we should get closer to this perfect 50-50 outcome. And we'll explore that and see what really we observe, because it's not quite the way that you might expect it to be. To start on our goal of describing a probability distribution, we first have to understand what a probability distribution function would even look like. So we can consider flipping 10 coins. Again, we're using coins because there's only two outcomes, and the small number 10 gets us something that we can more easily consider and comprehend. So what outcomes are we likely to observe? We can actually figure out the probability of getting any outcome using the following equation. So here we have our configuration that we discussed last time. This will tell us how many unique ways we can flip a certain number of coins. So n would be 10, and j would be the number of heads that we're interested in. We also call this the weight, and we use the symbol W here for weight. The weight is the same thing as the configuration here. It's the number of unique outcomes that give the desired result. If we want, we can convert the weight into a probability, and we can find the weight of our different outcomes. So here, the weight is the total number of outcomes that give us the thing that we want to see down here. So in this case, we could see that there are 252, you can't maybe see this from the graph, but you can do the calculation for yourself. There are 252 ways in which we could flip 5 out of 10 coins, and that is the most of any of the options. So that makes 5 out of 10 the most likely to be observed. However, 4 and 6 also have pretty substantial weights. So we have 210 out of 1,024 ways to get 4 out of 10 heads, and we also have 210 ways to get 6. And we can go down and see the different likelihoods of getting different things. So for example, if I told you that I flipped 1 coin at heads out of 10 total coin flips, you could look at this and go, what are my chances of actually doing this? And we can convert this weight into a probability, as you can see here. And what you end up seeing is that there's about a 1% chance that you would observe this. So if we got 100 students together and each of them flipped 10 coins, approximately one of them would have 9 tails and another one would have 9 heads. and you can do probability in this way. So it's not wholly unlikely. Now, the question we want to address is what is going to happen to our probability as we increase the number of coins we flip. Now, our intuition suggests to us that if we flipped 50 coins instead of 10 coins, we should be more likely to get 50% heads than under the 10 coin scenario. And of course, we would be shifting. So 50% heads out of 10 coins is 5, or 50% heads out of 50 coins is 25. But we should be nearer to 25 heads than we are to 5 heads. That's kind of the instinct that we have. We should be more likely to get that. Now, what do we actually see? We can plot this. Again, here we're plotting the weight, and we get weights that look like this. So the first thing we can note is that these weights are astronomically higher than our small system. So while there are only 252 ways to flip 5 out of 10 heads, there's greater than 1.2 times 10 to the 14th ways to flip 25 out of 50 heads, because there's so many more combinations of coins you can get with 50 than with 10. So it's kind of hard to visualize what's going on with the weight when the weights are so drastically different. Let's compare, instead of comparing the weights, we're going to compare the percentages and see what happens. And remember, our intuition is suggesting to us that we should have a larger percent chance to get 50% heads the more number of coins that we flip. Let's see how reality holds up to that expectation. Here we can see the exact same plots. This is the plot from last time, and this is the plot for the 50 coins, but scaled to represent probability, and also set to the same axis here, where the top is 25%. So for the 10 coin flip example, we have approximately 25% chance to get 5 heads, which is pretty good, right? That's 1 out of 4 people we would expect to get 5 heads. What about for the 50? Remember, our intuition is suggesting that this should be larger, but it actually is much smaller. So this could potentially be disturbing, right? Does this actually destroy everything we expect for probability? In this case, we can see I only have about an 11% chance of getting 25 heads out of 50. And I should be getting more, right? What's going on here? This kind of this contention can be hard to reconcile at first, but then we need to take a step back and think about what we're actually doing in this case. So what do we actually think is going to happen? We don't really think that we are more likely to get exactly 50% heads. And if we think about it, right, our chances of that should actually go down, because there's only one possible way to get exactly 50 heads. We have to get exactly 25 coins heads. And that's unlikely the more number of coins we flip. What we're actually doing is not increasing the chance that we will get exactly 50-50. Rather, we are decreasing the chance we get significantly different from 50-50. So what do I mean by that? Let's go ahead and look at some of this plotted in a table. So here we can look at the probability of getting 50%. So it's about 25 for 10 coins and about 11 for 50 coins. So it goes down. But what's the probability of getting near 50%? And so for the sake of being able to do this pretty easily, I set near 50% being from 40 to 60. So to do this, I simply summed up the percentages of 4, 5, and 6 for the 10%, and then 20 to 30 for the 50 coins. And so for 10 coins, we have a 66% chance, so a 2 out of 3 chance of getting either 4, 5, or 6 heads. How does that compare for a 50? Well, for a 50 coin flip, we have an 88% chance of getting somewhere from 40 to 60% heads. So what's happening in increasing the number of coins isn't necessarily that we're getting an increase in the likelihood of observing exactly 50-50, but we are getting nearer and nearer that 50-50 threshold. So another way to think about this is that the difference between 24 heads out of 50 and 25 heads out of 50 is much smaller than 4 to 5 out of 10 flips. And just to really hammer this home, we can also see what happens for 100 coin flips. So for 100 coin flips, we have only an 8% chance to get 50 heads. but we have a 96% chance to get somewhere between 40 and 60 heads. So we're getting a much narrower distribution. So one way we can view this is to try to normalize this distribution here onto the same scale as our previous one. And to do that, what I did is just took all of the ones. So I took like these 5 here that were the nearest whole number, and the percentage they were to is 50. So I added all these together, added these ones together for 40 and then 30 and so forth. And we get a plot that looks like this, where the yellow bars here are our original data for 10 coin flips. And then in the red bars are the 50 coin flip data. And you can see that what we get is a narrowing of this distribution. We are much more likely to observe near 50% heads, though not exactly 50% heads. The next thing we can do is convert these probability functions from these discrete variables to continuous variables. And we'll do that using the Gaussian distribution. And the reason for this, like we mentioned in the beginning, is that it's actually a pain to go through and generate plots like this. So for this plot, what I had to do is go ahead and use this equation here for every number between 0 and 50 heads. Now, Excel can be pretty helpful with that, so I didn't do it by hand, I did it using Excel, but that's still cumbersome. And if I wanted to analyze, 1,000 coins or Avogadro's number of molecules, this would not be very easy or fun to do. So instead, what we want to do is convert this into a continuous variable that we can use. This will allow us to analyze these things with relative ease. And so the variable that we will use is the Gaussian distribution function, and that can be shown here. So here, this p of x here, this is the y value, which is a probability. So if we take a physical x and plug it in, what this function will give us is the probability of observing that x, given a mu and a sigma. Now, what are mu and sigma? Mu is the average. So for a coin flip, that average would be 50%. And we can generate what mu is by multiplying m, in this case, m is the number of events, times p, the probability of a successful event. So for a coin flip, if we get 1,000 coin flips, m would be 1,000, p would be 0.5, and our mu would be 500. We would expect 500 coin flips to be the most dominant outcome. Sigma squared is the variance. And so the variance here is equal to m, the number of events, times p, the probability of success, times 1 minus p, the probability of failure. Let's compare this to our binomial distribution and see how it works. So I've done this for the 10 coin flip. In yellow, we have the 10 coin flip binomial distribution, and in red, we have a Gaussian distribution for the 10 coin flip. And what you can see is that it does a pretty good job at matching. So the staggering there isn't real, it's just an offset, so we can see the differences between them. The binomial distribution in some cases is overestimated by the Gaussian distribution, in other cases it's underestimated. So you can see that the Gaussian distribution tends to overestimate the extremities and also the middle here, and underestimate these intermediate regions. But for this example, it does a pretty good job at capturing it, even for the 10 coin flip. As we increase m, the number of events, our Gaussian distribution becomes a better approximation of the binomial distribution. So I did a chi-squared analysis, much like we've done for the solver function on Excel. And the chi-squared for 10 coin flips is 0.84, but for the 50 coin flips, it's 0.01, despite having 5 times as many things to sum together. So it gets more accurate the larger number of events that you attempt to describe. Here we see a probability distribution function that has been changed to account for a die roll instead of a coin flip. So let's go ahead and look at what we're doing here. In this curve here that's black, this is our probability distribution function. I've multiplied it by 100 here to convert into a percent rather than a fraction of 1. So what this curve will tell us is that we are most likely to get 1/6 number of successes. In this case, it can be whatever die you wanted to roll. Maybe it's a 6. And we could go to where it intersects the integers here to figure out how likely we are to observe certain outcomes. So with this plot, we can figure out how likely it is to get any specific outcome. Now, the most likely outcome is 1.667. That's obviously not a real outcome because we don't have a fraction of a die, but we can use this to figure these sorts of things out. So we have about a 12% chance of observing 0 6s out of 10 rolls. We've got about a 29% chance of observing 1. We have a 32% chance of 2, and then it drops off again for 3 and 4 and so forth. So only about an 18% chance of getting 3 and very low chances of getting anything 5 or greater. So this probability distribution function in the terms of the Gaussian function is actually pretty nice in order for us to easily evaluate what we have with die rolls, coin flips. Again, we can apply the binomial distribution to almost anything if we consider only success and failure as two valid options. I want to point out something interesting here is that these distribution functions also represent the best way to determine if an experiment is following the expected parameters. For example, you could consider a case where you think you might have a weighted die, right? Maybe someone is cheating you and the die you're using is more likely to be a 6 than it's supposed to be. And he's using that to scam you. So we could try to figure out what this would be. So one thing that you might think to do is say, well, I'll just roll the die a huge number of times, and then I'll figure out, am I getting an approximately 1/6 distribution of each of those? There's a problem with that, though. So if you use, say, a relatively small large number, that 1,000, if you roll the die 1,000 times, you would expect to get 167 of each outcome. However, using the Gaussian distribution, we can show that we're actually quite likely to observe anywhere from 148 to 185 of each individual outcome with at least 1% or greater probability. So if you rolled 1,000 dice, this die 1,000 times rather, and got 180 heads, you might think that something shifty was going on, the die is slightly weighted, but you couldn't really be sure because you have a reasonable chance of actually observing that. However, if we take it in a slightly different way and don't roll the die 1,000 times, but roll the die in sets of 10, 100 times and plot how many heads we got out of each set of 10, we can basically plot this distribution function and see if it matches. And this is a little bit easier. It gives you a more wide range of data than just a single number to say, are we actually matching the distribution? So if I plot this one here, this is the distribution that we would expect for a weighted die with an 18% chance to roll a 6 rather than a perfect 1/6% chance. And you can see that there are some significant deviations. So for example, in this weighted die, it's only about 11% likelihood to get 0 as compared to about 12.5. And then to get a 1, it's at about 26 instead of about 29. So if we rolled 100 sets of 10 and our rolls for 1 were closer to 26 than 29, and our rolls for 4 were closer to 7 rolls rather than 4 rolls, we might be able to better say, hey, this die isn't actually coming up like it's supposed to, right? This die seems to be weighted in some way, and we're getting this one outcome of a 6 more likely than it really should be by random chance. And of course, if this is more skewed, this is a very small deviation from 16% to 18%. If it was something like 25%, we would see the distribution would be totally different. And we would expect a very low amount of no 6s and a very large amount of 5 and 6 and 4 6s out of 10. So this is a much easier way to say we actually have an error here. And this die is weighted, or this coin is weighted, or this experiment isn't following the parameters that we think it should be. To conclude here, we've went over probability theory and used it to describe how likely an event is to occur. We mostly focused on things like coins and cards and dice. In the next few lectures, we'll start to apply this to molecular systems, because just like an individual roll on a bunch of dice can be made to be the probability of a bunch of different events, so can the total energy of the system be made to be the individual events of the molecules that are making up that system. We saw today that as the number of events increases, the likelihood of being near the average event, the expected event, becomes more precise. And we already saw how this worked for 10 to 50 to 100 coin flips. Once we apply this to Avogadro's number of molecules, we'll see that we basically can only observe one outcome, and that outcome is the dominant distribution. And we'll see that next time as first formulated by Boltzmann. And we saw that we can use, in a lot of cases, Gaussian distributions to describe these discrete variables in a continuous way.